last April talking about quantum computing, but today he's actually visiting Jilla for 2 weeks, so we had an opportunity to have him for another colloquium. So Steve probably needs no introduction to this crowd, but I'll say a few words. He got his PhD working with Hopfield at Princeton, and after that he went to NBS, spent 10 years working there in Maryland. After that, he moved to Indiana and built an amazing group in collaboration with Alan McDonald, working on condensed matter proper, solid-state physics, strongly interacting, many-body physics, but focused on quantum Hall effect for the most part, and that work was later recognized together with Jim Eisenstein and Alan McDonald by the Berkeley Prize of APS. Both Alan and Steve moved on in 2001, and Steve moved to Yale. We tried to bring him here, but he chose Yale. But this is but he's a frequent visitor here, and so that's the way we like it. He's also one of the founders of the Boulder Summer School, our beloved Boulder Summer School, that's now in the 25th year. So we're grateful to him for this. So today he is going to talk about, he's an expert on Josephson junctions and the kind of physics that was recognized at the center of this year's Nobel Prize in Physics. And so it's very appropriate to have him here to talk about that physics and the Nobel Prize. And so without further ado, Steve.
Thank you, Leo. Leo does all the work in the Boulder Summer School, so we're really grateful for how successful Leo's made it. I was very excited that my thesis advisor won the Nobel Prize last year, and my colleague Michel Devoret and his postdoctoral advisor John Clarke and John Martinis, who was a student of John Clarke at the time, was just announced as this year's winner. So I have to start with a funny story. As some people in the room know, the announcement is made at 11:30 a.m. in Stockholm, and roughly the first Tuesday in October. That's 5:30 a.m. on the East Coast and 2:30 in California. And an hour before that, they try to reach the laureates so that some of them can talk to the press after the announcement. So I'm in Blacksburg, Virginia, at Virginia Tech, for the dedication of their quantum building that Tuesday morning. 4:30 in the morning, my cell phone rings. And I look, and it was like a whole bunch of digits in the numbers. Oh, it's one of those foreign spam things. But I used to live in Sweden, and I said, wait a minute, it's 046, isn't that the country code for Sweden? I'm sure it's not for me, but maybe I should answer. So I answer the phone. This nice lady says, hello, I'm calling from the Royal Swedish Academy of Sciences. I'm sorry to wake you so early in the morning, but do you have Michel Devoret's cell number? So I said, yes, I do. And they actually had his cell number correct. They had tried to reach him, but he had his phone on Do Not Disturb. So a word to the wise, don't put your phone on Do Not Disturb in October. Okay, so it was a pretty exciting morning for me, I'll tell you. That was followed by, the APS, the New York Times called the APS, and they gave them my name, so then a bunch of people called. So it was a nice day. And, oh, thanks, Leo. So I'm going to try to talk about...
Smiley face.
Great. Is that good? OK. I'm going to try to talk about the physics behind this discovery of macroscopic quantum tunneling. And so that takes place in an electric circuit, and also quantization of the energy levels in electric circuits. So this is the beginning of constructing synthetic atoms out of electrical circuit elements involving, there's only 3 approximately dissipationless circuit elements: capacitor, inductor, and Josephson junction. If you allow for optomechanics where pieces can move, you can get another nonlinearity that way. And we want to avoid dissipation so that we don't have decoherence. So let's remind ourselves about tunneling. So classically, as a particle is moving along at constant total energy, it has kinetic energy and potential. And the potential energy rises as you climb you're in a car coasting maybe, or a bicycle, and you're going up the hill. You're losing kinetic energy, and you're gaining potential energy. But at some point, you've lost all your kinetic energy, and it can't become negative. And therefore, you're at the classical turning point. You have to stop and turn around and go back. And it's impossible to come out on the other side of the hill unless you have enough kinetic energy to go over the hill. But bizarrely, in quantum mechanics, the way a quantum particle gets through the hill is it just makes its kinetic energy negative under the barrier. You say, what? How could kinetic energy be negative? Well, let's remind ourselves that the kinetic energy operator is minus some numbers times the second derivative acting on the wave function. And if you have a plane wave like e to the I kx, the kinetic energy is h bar squared k squared over 2m. And e to the I kx is an eigenvector of that. If you have imaginary momentum, so k becomes imaginary, and the wave function becomes e to the minus kappa x, it has negative kinetic energy. And so it goes along at constant energy, even into the classically forbidden places, but the amplitude is falling off exponentially. So there's only a small probability of getting through the hill, but you can get through the hill. OK? So that's like a mechanical analog of what's going to do the tunneling in an electrical circuit. The circuit is not physically moving, but some parameter that describes the circuit is going to move. So good. So let's start though with a little bit about remind ourselves about quantum mechanics, and if you have a 2-level system like a qubit, the quantum information is carried in the complex numbers that describe the superposition of 0 and 1. And if you wanted to build if you wanted to gain quantum control of this object and maybe use it to build a clock or a computer, you have to be able to control those superpositions. And you have to have an energy spectrum which is anharmonic, so that the blue light will say let you move between 0 and 1, but it's off resonance to the next level spacing, unlike a harmonic oscillator where it would be equal. And then you can't Rabi-flop between those two. It's very important to have an anharmonicity. So this will become part of the story when they measure quantized energy levels. It's hard to see quantized energy levels in a harmonic oscillator unless you can measure something quadratic like the energy. So, and the other thing, we like to talk about our synthetic atoms. I have some of my best friends are atomic physicists. They're very fond of natural atoms. They have nice features, like they're not just identical, they're literally indistinguishable. You can trade places of two of them, and the wave function is the same, possibly up to a minus sign. But they're small. You've got to do all kinds of stuff with lasers to hold on to them. You can't really engineer their individual properties. And the natural atoms have amazing coherence properties, but that's because they don't couple to the outside world very well. That makes it hard to couple to your control system, possibly to your measurement system. People have made lots of progress overcoming this, but there's a sort of natural optimization struggle in quantum engineering between controllability and coherence. If you can control the qubits, so can the noise demon. That's the problem. Okay, so there's a bunch of pros and cons. These synthetic atoms, we can attach antennas to them. We can change their size. We can change their transition dipole moments. We can adjust their frequencies. Lots of things. On the other hand, they're not all identical, and if we can adjust things, so can the noise demon. Okay, so now that's sort of where we're going to end up with at the end of the history. So here's the beginning of the history. Josephson junction is just two pieces of superconducting metal, typically aluminum, separated by a nanometer or two of aluminum oxide, in quotes, so some nasty amorphous stuff, but it's an insulator. And electrons see a potential barrier that's very high, and they can't go through the insulator, at least as classical particles. But as waves, they can tunnel through. And in a superconductor, the electrons are in pairs, spin up and spin down. And amazingly, they can coherently tunnel as a pair from one sort of bosonic condensate of pairs in this electrode into a bosonic condensate of pairs in that electrode. And the order parameter, the thing that describes the superconducting state, where all these pairs of electrons condense into a single giant macroscopic wave of some roughly fixed amplitude, but the phase is adjustable. And we'll be talking a lot about the phase across the Josephson junction, the phase difference between the condensate here and here. So let's imagine the kind of electric circuit that people that were playing with Josephson junctions many decades ago were using. So here's a current source. There's also a microwave source, but we'll skip that for now. And the current IB, the bias current, is flowing out of here, and it splits into three arms. There's some resistance. That may actually be intentional, or it might be a transmission line that's attached to this that has an effective impedance. It can be various things, radiation impedance. There's current can flow and charge the capacitor. And then current can tunnel through this tunnel junction. The actual tunnel junction is between the plates of the capacitor, but for circuit drawing purposes, we pretend it's a separate element, right? So no leakage through this capacitor, but coherent tunneling through this object. Okay, so then we'll define this phase, phi, as the phase difference across the junction. And we'll write down what happens to this current. Well, it turns out that the current that flows through the Josephson junction is some maximum possible current, I0, called the critical current, times the sine of the phase difference. Okay? So the biggest that sine can be is plus or minus 1. So the most current that can possibly flow is this critical current, I0. Then if there's a voltage across here, then there's current flowing through the resistor by Ohm's law, V over R. And then if the voltage is changing with respect to time, there's some displacement current charging up the capacitor, right? And so the sum of those three branch currents has to equal the total current supply, okay? So that's one equation. The other equation brought to us by Brian Josephson is that the Planck's constant times the time rate of change of the phase, which is a frequency, so it's like h bar omega, is an energy, namely the charge of a Cooper pair times the voltage. Okay? So this equation tells us about how much current is flowing, and this equation tells us how the phase changes given that there's a voltage. Okay? Is that clear? Great. So you can then just take another time derivative of this equation, plug in some results from this equation, and get Newton's law for this particle whose position is this phase phi. Okay? So the time rate of change of the charge on the capacitor, let's say, is ddt of the charge times the voltage. The voltage is the time derivative of the phase. And so you end up with this thing, which looks like mass times acceleration of the particle should be equal to the total force acting on the particle. And it turns out, when you use all the terms from this equation, that there's the bias current produces a constant tilt of the potential, so a constant force. This term produces, which you can think of as a conservative force, the derivative of some energy with respect to position phi. The energy stored in the Josephson junction is a number times cosine phi. So the derivative with respect to phi, the force, is sine phi. And then you have viscous damping, 1 over r times the voltage. That's phi dot. Okay, so Mike Tinkham, one of the great heroes of early developers of this kind of physics, likes to draw this blue curve, which represents the potential energy landscape on which this particle phi, so this is the coordinate phi, that's like the position of this fake particle describing the phase of the condensate. And he said, oh, this is a washboard potential. And then he says, for those of you who don't know about washboards, there were these things with metal, and when you rubbed clothes on them in the creek and you cleaned them. But if you've never seen one, just think of it as a classical analog of a Josephson junction. Okay. So the particle is moving in this potential. It has mass given by the capacitance. The slope of the potential is the bias current. The corrugation's given by the critical current. And then possibly, if it starts moving, there's dissipation. There's friction, because there's a force trying to stop the acceleration. Okay? And so if the particle were sitting here at the bottom of this well, if it were a classical particle, it would just sit there as long as the temperature is very low. Maybe occasionally some thermal fluctuation would move it over the hill, and then it would start rolling down like this. And when it begins to roll, the phase is changing with time, and that means suddenly there's a voltage. If you had a superconducting circuit, current can flow with no voltage, for example, just by I naught sine phi. But suddenly there's a voltage. And that's how we're going to detect the escape of the particle from this well. And the experiment that won the Nobel Prize was to do something like this, but cool it down very, very cold just get extremely paranoid about filtering electrical noise down from room temperature. They had to invent copper powder filters and all kinds of stuff. And they found that still, if you put the particle there and you waited, all of a sudden a voltage would appear that you could measure, a macroscopic voltage. And that was quantum mechanical tunneling of this particle through that barrier. And you can make the barrier weaker and weaker by just tilting, putting more current and tilting this, making it easier and easier to tunnel out. Okay, so where did that idea come from? It came from Tony Leggett around 1980, another Nobel laureate who won actually for his theory of phases of liquid helium-3. But he asked the question, if the junction phase, the phase across the junction, acts kind of like the position of a classical particle, could that particle itself become somehow quantum mechanical? And how do we just decide if that tunneling event occurs, how macroscopic was the object that tunneled? You know, if we're pretty sure that we can't tunnel through that wall. We're too big. There's too, you know, I wouldn't recommend trying it. And we know that very small things can tunnel. But how do you know, when this superconducting circuit rearranges its state and the circuit contains trillions of electrons, how big do we how macroscopic do we decide it is? And so he speculated on these questions in 1980. And it's kind of a subtle question. So first off, like the phase of the condensate, why in the world do we think this feature of superconductivity is somehow classical? I mean, it's a whole quantum theory of how superconductors form. They form this condensate. It seems very quantum mechanical. But you have to be careful. So Michel, this slide is from Michel Devoret. He likes to use the following story. You know, you can look, it was known to the ancient Greeks that when you looked at crystals and you saw these facets, it seemed consistent with having stacks of little balls in certain lattice structures with cleavage planes, and that was evidence for the existence of atoms. There's, of course, now we know there are huge quantum effects that hold the atoms together. They're covalent bonds and ionic bonds and all kinds of fancy quantum mechanics happening to hold this crystal together. But it's so strong, the energy gaps created by that quantum effect are so large that basically the only interesting degrees of freedom left are the center of mass position and maybe some rotation. And so what we mean by macroscopic quantum tunneling when we have an electric circuit with trillions of electrons in it is superconductivity formed and did all kinds of fancy quantum mechanics, but now it's described by all the electrons being in some basic state with the same phase. That's like describing what the center of mass position of this crystal is. And the macroscopic quantum tunneling would be if the 0 point uncertainty in the center of mass position caused this to fall over in gravity. So when it starts to fall over, the potential in the center of mass has to rise a little bit and then fall. So there's a barrier it has to go through. And you would be very surprised if a macroscopic piece of galena like this would actually tip over, right? And you would, if it did tip over, you'd spend years looking for sources of vibration in your table and you know, getting rid of all these things. So this is what these guys had to do in their experiment. And these experiments were attempted at Bell Labs and IBM unsuccessfully before them. And these guys were sufficiently, you know, they were super experts on Josephson junctions, super paranoid about filtering and just being incredibly careful and doing many, many control experiments to make sure that what they were seeing was really quantum mechanical. So here they are some time ago. Michel, as I said, was a postdoc with John Clarke. John Martinis was a graduate student. And they had a Josephson junction lab. And they said, you know, this would be great to test Tony's ideas. How can we do it? And 5 years after Tony's paper, they published 2 now famous Physical Review letters demonstrating macroscopic quantum tunneling and quantization of energy levels in electric circuits for the first time. So here is a little piece of that corrugated potential with the slope caused by the bias current. And if you cool down to very low temperature and don't have any noise, then the particle will sit here in this anharmonic potential. And the barrier height and thickness is too large for the phase particle to tunnel through it. It'll just sit there. But if you went up to an excited state somehow, maybe the barrier is lower and thinner, and you can tunnel through. And so the first experiment was just increasing the bias current, tipping it like this to just, even though you're sitting in this state, you lowered you made it easier to tunnel out by making the barrier lower. And so they would set the bias current and wait. And after some length of time, inevitably, suddenly the voltage would appear in the circuit as it ran down the hill. And you had to have amplifiers to see it and stuff, but it's basically a macroscopic voltage. And so that was the first evidence of tunneling. And then the evidence for quantization of energy levels is they lowered the bias current so that this guy never tunnels, but this guy does tunnel. And then they shone microwaves in the gigahertz region to excite this atom from its ground state to its first excited state. And then it would more quickly tunnel out. And you can see they didn't vary the frequency of this tone in order to do spectroscopy. I think they had a fixed frequency, but they varied the tilt, which varied the curvature here and varied the transition frequency until it matched the microwave drive. And you would see, as a function of the bias current, a series of peaks in the rate at which how long it took on average for the voltage to appear, the tunneling rate. Okay? Yes?
Do they see, in typical experiments like this, do you see also AC part from the washboard frequency?
Yeah, so once the particle tunnels out, it begins running downhill at not exactly a constant rate because it is corrugated, but roughly a constant rate, which is limited by the resistance in the circuit, the viscous drag. So there's the force and the viscous drag, and it comes roughly to equilibrium. And then,
the DC part.
Yeah, and then that means the phase is winding at a certain rate. Then the corrugation, the modulations in that rate produce AC voltages.
So is that something that people see?
Yes, yeah. But they prefer to see it in a more non-dissipative, a slightly different experiment. But if you put a DC voltage on a Josephson junction and the Cooper pairs can't really consistently tunnel unless the voltage is 0. And so the phase ends up winding at a rapid rate, and the current is sine of the phase, so you get an AC current at very high frequencies proportional to the voltage. And as a wise person once said, the only thing you should measure is frequency. So John Clarke got his start by building the world's most sensitive voltmeter by measuring the AC voltage from that. So that's where his experience came from, the Clarke slug. So as I said, there are three in the engineers, the synthetic atom kitchen recipe book, there's the inductor, the Josephson junction, and the capacitor. And nowadays there's also mechanical motion for optomechanics at both microwave frequencies, as is done here in Boulder, and optical frequencies, also done here. And so you can play around with different sizes, different numbers of junctions in series and parallel, and make your own little periodic table of the synthetic atoms. The Cooper pair box, where the capacitance is very small, and the Josephson energy is very small. Large series arrays of Josephson junctions, all different kinds of qubits that have to do with the ratios of these parameters. So design your own atom. And people have done all this, and all of this has flowed from these initial experiments in the Clarke group. So let's start with the Cooper pair box. So now we're going to talk about one thread of the history. So imagine here's my Josephson junction, the insulating tunnel junction. Here's my two wires, except this is not a full wire. It's just a little tiny chunk of superconductor, very, very small. And there's a bias voltage that you can put on this gate to make it easier or harder to get more charge onto the capacitor. And you might put an electrometer over here that is very, very sensitive. For example, Rob Sholkoff's radio frequency single electron transistor can measure small charges of order, with a sensitivity of 1 electron per microsecond or something, square root of a microsecond. And these are superconducting, and the charge, the Cooper pairs, can tunnel back and forth across here. And you're going to look at a situation where there are 1 billion Cooper pairs here, or 1 billion plus 1, roughly 1 billion. Larger circuits have trillions, but these had a few billion. So imagine two states. This guy is, all the electrons are paired up together. They're in a superconducting ground state, and they're either 1 billion pairs or 1 billion plus 1. And as a function of this gate voltage, the billion and the billion plus 1 will be different in energy, because, let's say there's 1 billion compensating nuclear charges in there. So 1 billion is neutral, and 1 billion plus 1 has charge. And you've charged the capacitor, that costs you substantial energy. Then you put a positive voltage on this gate, and you pull that guy down, and this guy is either horizontal or going up, the details. And you can make the levels cross. So 1 billion and 1 billion plus 1 can become degenerate. And then you have two degenerate levels, and they're connected by a matrix element of tunneling through this Josephson junction. And it lifts that degeneracy by an amount by what's called the Josephson energy, which is related to this critical current that the junctions have. And so this experiment came from the group that Michel Devoret set up in Paris after he finished his postdoc in Berkeley with John Clarke. And this provided indirect but strong evidence for the box being in a coherent superposition of 1 billion and 1 billion plus 1. And you could continuously change the amplitudes, alpha and beta, for those two charge states by changing the gate voltage. And they measured with an electrometer the average charge on the box, which is going back and forth faster than your bandwidth. So you just see the average. And there's a smooth transition from 1 billion to 1 billion plus 1 to 1 billion plus 2 pairs. And the fact that this has a width which is not related to temperature, Fermi-Dirac statistics, and things like that, as you would see in a normal metal. In a normal metal, there's no coherent tunneling, only incoherent tunneling. And that width just goes to 0 as you lower the temperature. Here, that width goes to the Josephson energy. So that was the first indirect but fairly convincing evidence that you could have a superposition of different charge states, and that would allow the construction of what's called the Cooper pair box qubit. It's a bad idea, however, to have a qubit whose an atom that has a permanent dipole moment, because then it's the energy splitting is controlled by this gate, and stray electric fields, you don't totally control the voltage on that gate. So that was one experiment. Then Yasu Nakamura, who was at NEC in Japan at the time, decided he would try to move the gate voltage from here to here in 20 picoseconds and 40 picoseconds. And his friend down the hall had a $500,000 picosecond pulse generator. So he went in at night and stole it, apparently. No, he borrowed it. And he moved the voltage from here to here. So down here, you're in the state with 1 billion Cooper pairs and no fluctuations to 1 billion plus 1. Then you suddenly move to the degeneracy point. These eigenstates are 1 billion plus 1 billion plus 1 and 1 billion minus 1 billion plus 1, right? It's a coherent superpositions of those two possibilities. But he moved here to neither of those eigenstates. It's in a superposition of the two, and you began Rabi oscillating. It's as if you had a qubit and you suddenly turned on a drive field which looked like a magnetic field in the x direction, which rotates the qubit. In this case, it's a voltage. And here you can, then he had a very complicated but clever way to measure the oscillations in the charge, which is too complicated to explain. And here you see his results. So this is the gate voltage. And here you see this thing Rabi flopping for, a few hundred picoseconds. So it's not, not the greatest qubit ever. But this was the first time that you had real-time oscillations that were at least the beginnings of quantum control. But it was only Rabi oscillations, and we'll come back to that. And then in Delft, Hans Moy developed a different circuit called a flux qubit, where the two states are not charged, but whether there's a current flowing in the loop this way or that way. Pretty big currents, actually, macroscopic currents it's not a full microamp, but it's bigger than a nanoamp, I think. 10 nanoamps or something. So, something you can measure with a nanoammeter. That was a whole nother way to do things. It turned out to be very sensitive to flux noise. So in the end, while it was an early success, it didn't really develop as super useful. But then the next great breakthrough came from the group that Michel, Daniel Estève, Denis Villon, and others in Saclay and outside Paris, where it's very French. They sat down and said, let's design like the ideal atom, and it should have some control knobs like that gate voltage that I showed you. It also should have some kind of loop and we'll put magnetic flux through it. So I have two control knobs, and it should have a clock transition point, a place where its transition frequency is insensitive to both electric field, no Stark shift, and no Zeeman shift. And so then they would sit right there, and it should have much longer coherence time. And sure enough, it did. And it's a kind of complicated circuit. It's got a balanced part and an unbalanced, a differential and common mode, and the readout. Oh, it's just amazing, but it's too complicated to explain. But as a result of having this clock transition, suddenly they were able to do not just Rabi flopping, but Ramsey fringes, where you take the qubit, you make a pi/2 pulse, the superposition processes another pi/2 pulse. You then measure the state, and you see, just like is done in an atomic clock these days, you see Ramsey fringes lasting half a microsecond. So it's suddenly 1,000 times better because it has this sweet spot. And they had a kind of clever quantum non-demolition readout scheme, although it wasn't that non-demolition. But it was clever. So that was just before, this was published in 2002. The experiment was done in late 2001, just before Michel moved to Yale. So so then, okay, even skeptical atomic physicists would have to agree that this is an evidence of true coherent superpositions in an electrical circuit. At least I hope they agree. So then here's John Martinis, very quickly, just based on the exact experiment he'd done as a graduate student, worked on this phase qubit. So he had the bias current. He had these quantized energy levels that he observed in his thesis. But he made the well deep enough so that neither of these levels would tunnel out into the finite voltage state. And then there was a third level that would tunnel out. And so he could manipulate with Rabi flopping this coherent superposition. And then he could measure whether he's in the excited state by applying a microwave tone at this frequency and move the population up here. It would quickly tunnel out and produce a massive millivolt scale voltage. This is just his thesis over again with one extra level. And he achieved an 85% single shot readout fidelity, which at the time was just a huge advance. But then when he tried to do it with 2 qubits, that when you read out one, this huge voltage and all the AC voltage from the particle rattling down the washboard wiped out all the other qubits. So it was a highly destructive readout. So another great idea bites the dust. Okay, so now let's talk about cavity QED ideas applied to electrical circuits. So, probably everybody here knows about this, but, when you first learn about the hydrogen atom, there's a 1s stationary state, a 2p stationary state. They live forever. But then you find out that actually the vacuum fluctuations of the electromagnetic field actually do things to that state. And in particular, they give it a finite lifetime of about 1.5 nanoseconds. So that's not so good for a qubit. It emits an ultraviolet photon. It also gives you a Lamb shift splitting between the previously degenerate 2s and 2p levels. And the whole name of the game in cavity QED is to change the spectrum of electromagnetic fluctuations, the vacuum noise spectrum, to engineer it so that interesting things happen, like the Lamb shift changes, you get cavity shifts. The lifetime changes, you get the Purcell effect. And so you can use optics, or you can use microwave light and completely surround. Instead of mirrors, you can just put a hole in a box and surround it with superconducting walls that reflect the microwaves. And if you make the box, if you put a qubit inside the box and the qubit wants to spontaneously emit a photon. So let's say I have a transmon qubit, which I'll talk about later, in free space. It's got an antenna 1 millimeter long, and there's, it just spontaneously would emit a microwave photon in 100 nanoseconds, just like hydrogen, only slower. Okay? But if you put it inside this box and there's no mode at its frequency, the lifetime goes up by a factor of 1,000. And that's the Purcell effect. There's 2 Purcell effects. When you're on resonance, the lifetime goes down. When you're off resonance, the lifetime goes up. We want to make it last longer. So we live by this factor of 1,000, getting from half a microsecond to 500 microseconds, now even a few milliseconds these days. So that's, so you engineer the spectrum of vacuum noise and it changes how the vacuum interacts with your atom. So, so here is the gang in 2004-ish. There's Rob Sholkoff, Alexander Blais. As usual, Dave Schuster is asleep on his feet, and Andreas Wallraff. And the whole gang is photographed inside Rob's, we called it Rob's skiff, for those of you who know what a skiff is. It was a big copper box. And the idea was that these qubits have the same transition frequency as your cell phone radiates at, 5 gigahertz. And so maybe we should protect everything from that. Well, it turns out you don't need that. And eventually, if you know how to filter things, you don't need that copper box. And so the first experiments were done in here. And I got involved when I moved to Yale, and Rob and I had this discussion about, isn't there some way you could do the analog of cavity QED? And eventually we figured out, for example, how to read out a qubit by sending microwaves down a wire to this resonant cavity and then bouncing them off. And the qubit has, the cavity is approximately dissipationless. The qubit has a different frequency. And so nobody can absorb that microwave photon. It has to come back. The only thing that can happen is that it can develop a phase shift. And the phase shift depends on the frequency of the cavity relative to the frequency of the photon. And the frequency of the cavity, it turns out, has a dispersive coupling to the qubit. The frequency of the cavity depends on the state of the qubit. And so by just you send in, so let's say we put the qubit in the x direction on the Bloch sphere, a superposition of up and down, 0 and 1. And then there's some coherent state alpha of microwaves coming down. And after the interaction, you're in an entangled state between the microwaves and the qubit. If the qubit is up, the microwave phase, the coherent state has this phase. If the qubit is down, it has a different phase. And this is how, I mean, I learned so much from this. I didn't know how quantum measurements worked at the time, nothing. But you entangle, you don't actually do a projective measurement directly of the thing you want to see, the qubit. You entangle the qubit with a meter, and then you measure the meter. In this case, the meter is the phase of the microwave coherent state. So we published this theory paper in 2004, just at the end of the time when you could write crazy ideas and get them published in certain, I won't call them journals, magazines. And we made the mistake of saying, and this is going to work, and the experiment's underway. And the referee said, OK, send us the experiment. So we did the same year. And so here is the vacuum Rabi splitting, where you make the cavity and the qubit have the same frequency, and you see that this is the spectrum as a function of some tuning parameter. And the cavity photon, eventually that line becomes the qubit as it crosses, and the qubit becomes the cavity. And here, the eigenstates of the system are 1 over root 2 photon in the cavity, qubit in the ground state, plus no photon in the cavity, qubit in the excited state. And this is the upper polariton, lower polariton, or as Dave Schuster called them, the Q-ton and the faux bit. And then if you move the qubit away from the cavity frequency, then you have to do, not much happens, but in second order perturbation theory, you get this dispersive pull of the cavity frequency by the state of the qubit, or conversely, the qubit suffers a light shift for each photon that's added. So this is a spectrum. This is a quantum jump spectrum of the qubit. So this is the probability that the qubit changed its state, which we measure with a separate readout. We don't measure the absorption of the microwaves to do spectroscopy like shining a laser through a gas. We do quantum jump spectroscopy, where we shine a little bit of light and then we measure the qubit. Did you change state? And you see a whole series of peaks with a constant frequency shift between them, depending on whether there's 0, 1, 2, 3, 4, 5, 6, 7, 8 photons in the cavity. So you can now count individual microwave photons. You discover microwaves are actually particles, right? They come in quantized energy lumps. And this was, yeah, I don't know. We were pretty excited by this data. The theory involved Jay Gambetta and Alexander Blais. The three-dimensional cavities came from Matt Rager and Honey Pike. So what is the sort of standard, what's the industrial standard qubit right now? I see I'm falling behind, but it's this transmon. Here's a piece of sapphire substrate, just a super good insulator. We wish it were even better. It's a millimeter in size. It's a dipole antenna that resonates at 5 gigahertz, but it's only a millimeter long. How can that antenna resonate? It's too short. You load it down with a big inductive loading in the center, whose name is Josephson junction. Josephson junction acts like a kind of nonlinear inductor and gives you these quantized energy levels that are anharmonic. And this qubit there's a lot of capacitance, so not much charging energy, and the 0-point uncertainty in the number of tunneled Cooper pairs from one side to the other is of order 3 to 10. And that turns out to make it very insensitive to electric field noise, because the charge is already so uncertain. And that gave much longer coherence times. It's like an artificial atom with an atomic number of about 10 to the 12. It's much bigger than a Cooper box, so 1 trillion Cooper pairs. And the spectrum is simpler than hydrogen, no fine structure. Has about the same Q as the hydrogen 2p1s transition, a few million. And it only can be, these state transitions can only be detected if you use dispersive readout. You can't use charge, because the charge is so uncertain. Other people, John Martinis and Andrew Cleland, and this was Max Hofheinz's either thesis or postdoc experiment, I forget. They produced, using now quantum control, weird superpositions like 0 plus 5 photons in the cavity, and they measured the phase space distribution, this Wigner function. This is theory, and that's experiment. So people were beginning to be able to exert quantum control over these synthetic atoms. In 2009, then Rob Sholkoff constructed the first sort of all electronic, I don't want to call it a quantum computer, but quantum processor maybe. It had exactly 2 qubits, one here, separated by a meandering superconducting resonator line, strip-line resonator. And they communicated with each other, and we performed gates by the exchange of either real or virtual microwave photons between the 2 qubits. And this was the first device on which you could run quantum algorithms. And we ran all possible quantum algorithms you can do with 2 qubits. There are 2 of them, Grover search and Deutsch Joseph. But OK, it's a start. And really, the current industrial systems based on superconducting qubits are massive, non-trivial scale-ups of this first device within the Jerry Chow and Leo DiCarlo experimented on. Other crucial technology had to be developed, quantum-limited amplifiers. You know, there's a kind of uncertainty principle that if you amplify a signal, the sine and cosine quadratures are canonically conjugate. They don't commute with each other. You have to add noise. And the best amplifiers add half a photon, essentially. And this development by many people, some in the room here, there you are, really helped advance the field and allowed very sensitive readout. It allowed Michel and Zlatko Mineev to do this amazing experiment with a 3-level system, catching and even reversing quantum jumps in mid-flight, which could have separately won the Nobel Prize, I think. And people are now looking for dark matter using these kinds of amplifiers. And we may never build a quantum computer, but maybe we'll discover dark matter. And now, through 20 years of engineering and what we call microwave hygiene, getting rid of all the microwave modes and the things that could cause dissipation, the dissipation is so low that we had to do something desperate. We had to turn to materials scientists to help us figure out how to make them even better. And Nathalie de Leon is the guru of this at Princeton. And tantalum, replacing some of the aluminum with tantalum, turns out to help a lot. Nobody knows why. It could be that the way it bonds to the sapphire is better, or maybe it's more refractory and you can put nastier acids on it to clean it, and maybe that's all it is. But anyway, it's better. There's now been, we've had an exponential growth in coherence time by about 6 orders of magnitude since 25 years ago. And Nakamura, well, didn't really have, maybe had nanosecond coherence or something, not really measured. And so better materials. And now the errors are slow enough that you can begin to do quantum error correction. That's a whole nother important story. People are now doing precision single qubit and 2 qubit gates with lots of 9s. Here's an example from Will Oliver at MIT. So we're really, desperately trying to imitate our atomic physics friends and build up precision quantum control of these objects and then perhaps assemble them into a quantum simulator or a quantum computer. I'm sort of out of time, so I'll just say error correction is the current grand challenge. You need to take a whole bunch of qubits and entangle them and store the logical information in some clever way so that even if one of the qubits gets measured by the environment, it doesn't learn what logical state is being stored in the qubits because information is all in multi-qubit correlations. We prefer a different approach where you don't use material objects as the qubits, but superpositions of different microwave photon states in high-Q resonators. Those are called bosonic qubits, and we've invented various codes, and other people have invented codes to do that. And the first experiment with quantum error correction for memory that sort of reached break even, that is, the logical qubit had the same or slightly better lifetime than the best of the individual components making it up, was done not so long ago, 2016, in Rob Scholkoff's lab, where they basically broke even or maybe got 10% over, using this amazing GKP code, which is this is a phase space plot, position of the oscillator, momentum of the oscillator, and you make a lattice of probability amplitude in that phase space. And it takes pretty good quantum control to be able to make something like that. And we're fantasizing that then a whole array of these bosonic qubits could be concatenated into a surface code or a color code or some other standard qubit code. So lessons learned: avoid DC like the plague, microwaves rule. Microwave hygiene: the only impedances that are allowed are 0 and infinity. Otherwise, there's dissipation. Once microwave hygiene is under control, you got to talk to Natalie and figure out about materials. Use clock transitions that make you insensitive to charge and flux noise. For the first 20 years, it was just keep the fab as simple as possible so we didn't have to think about it and we could concentrate on the microwave hygiene. And then, the atoms are gigantic. They talk strongly to the electromagnetic field and to each other. So couplings that you want or don't want are more or less always on. You have to learn either how to turn them on and off or live with them. And we've learned that bosonic codes can replace rather complicated and still outperform very complicated qubit-based codes, on which, though there has been great progress on qubit codes. My colleague Shruti Puri is teaching us that not all errors are created equal. They have some noise bias, and you want to build codes that take advantage of that. So here I'll just close with a picture of the gang from a few years ago doing some Robbie flopping with their hands or something. And where are these people now? So Dave Schuster is a professor at Stanford. Jerry Chow is the head of hardware at IBM, quantum. Jens Koch is a professor at Northwestern. Jay Gambetta is the vice president for all of research at IBM. Andrew Houck is the dean of engineering at Princeton. Rob is a winner of various prizes, and he won a big one. So that's my story about the history. Thank you.